Computing relies on a continuous interaction between two entirely different states: the physical architecture of hardware components and the intangible logic of software instructions. Connecting these two domains requires an operating system, a localized environment that acts as a universal translator between the electrical signals of the machine and the written commands of the user. To write effective code, a developer must first understand exactly how those tangible hardware components execute abstract logic. We begin by mapping the physical environment itself, tracing how data moves from long-term storage into active processing. Next, we examine the universal logic path that controls that movement, the input, processing, output sequence. Finally, we apply the rigid, 7-step engineering cycle required to build systems that scale reliably. This connection between physical circuits and logical flows is the defining principle of systems engineering. Every execution environment relies on 3 foundational components: the CPU, RAM, and storage drives. The architecture managing these components is divided by a single, uncompromising physical constraint: what happens when the system loses power. This chart compares memory types. On the right, non-volatile solid-state and hard disks permanently retain data. On the left, volatile RAM provides high-speed workspace for the CPU, but depends on continuous current. If power is cut, data in volatile memory is wiped out completely. This hardware reality directly dictates software design. Programs must be written to actively manage the state of their data to survive sudden interruptions. Because the active execution space is volatile, software must be explicitly architected to move information meticulously between temporary workspaces and permanent storage records. To shepherd data safely through that hardware, we use a rigid logical architecture. This diagram illustrates the input, processing, output sequence. First, the input phase accepts raw data for use. In the middle, processing takes over, executing calculations and logic. Finally, the output phase converts process data into results, displaying them or writing them securely back into non-volatile storage. Whether executing a simple web script or running a massive financial database, this loop is the continuous heartbeat of the software. Mastering software development requires complete command over how data moves through this specific, unchanging architecture. We command that input, processing, output cycle using syntax, the strict grammatical rules of a specific programming language. This graphic shows the identical instruction written in 3 different languages. Python, C++, and Java each enforce unique structural rules, but they achieve the exact same output of printing text to a screen. Hardware cannot read human code. Before execution, these text-based instructions must be translated into electrical signals by a compiler or an interpreter. This chart compares errors. On the left, syntax errors are structural mistakes caught during translation that prevent the program from starting. On the right, logical errors bypass translation because their grammar is perfect. Occurring at runtime, a flawed formula executes successfully but generates incorrect output. Syntax errors will annoy a developer by refusing to compile. Logical errors are catastrophic because they hide silently inside a fully functioning application. Preventing silent logical errors requires a rigorous methodology practiced well before the first line of code is ever written. This diagram maps the program development cycle, a 7-step framework designed to manage complexity and identify flaws at the source. Step 2 of the cycle relies heavily on desk checking. Developers manually trace the logic on paper, tracking a variable like my_number as it enters the input phase, gets processed by a specific formula, and calculates an output. Only after the logic is proven sound does the sequence move into actual coding, rigorous edge case testing, deployment to live environments, and long-term maintenance. A disciplined lifecycle ensures that fatal flaws in reasoning are exposed and corrected on paper long before they reach the physical hardware. Writing software is an exercise in applied systems engineering. Abstract human logic has to be meticulously planned, tested, and mapped into perfectly rigid syntax. That syntax is then bound by the uncompromising physical constraints of the machine, passing through volatile memory to be executed by the processor. By enforcing a strict development cycle, we bridge the gap between conceptual logic and physical architecture, reliably transforming raw data into meaningful action.